So, John just told you about everything that the LSST is going to be able to observe in the sky if we image it if we envision it just as a static sky with nothing changing. I'm going to tell you about all of the cool science that we're going to get out of LSST when we look at each of the things that change over the course of each night. So, a little bit of introduction. In 1929, Edwin Hubble looked at 24 galaxies and was able to observe by simply plotting a line along this plot that the universe is expanding. So he found that all of the galaxies that he observed were moving away from us. That doesn't mean we're at the center of the universe. That actually means that the universe itself is expanding. So this opened up the field of cosmology, which involves mapping the history of the universe. And by mapping the history of the universe, we can infer what the future of the universe is going to be. And so here, for example, is 4 different potential histories of the universe. And so if we observe the universe now or in the past, we can look back in the past because light takes a long time to reach us if we look at distant objects. We can determine, is the universe just coasting? Is it just expanding at a uniform rate? Or is potentially all of the matter that's in the universe, all the gravity from the matter, causing the universe to eventually slow down and recontract, and so that eventually it'll end up in a big crunch? Or, and this was initially a long time ago, thought to be unlikely, could the universe be actually accelerating or increasing in its rate of expansion? So it turns out that Edwin Hubble used galaxies because that's what he had the tools for and the telescopes for, but more recently, scientists were able to determine that supernovae, these exploding stars, are an excellent tool for mapping out the universe. They can be seen to very large distances. They can outshine, a single explosion can outshine an entire galaxy. They can be used to map distances very precisely because they all have roughly the same brightness, and so they can be considered to be like light bulbs that you can use to map out their distances. And so in the 1990s, I'm taking a chance here and showing you a plot. In the 1990s, scientists did the same kind of experiment that Edwin Hubble did. Basically, here's the scale of that previous plot that I showed that Hubble used to figure out that the universe is expanding. Scientists use supernovae to look much more distantly to identify on the order of 42 supernovae in the distant universe, and to map the expansion of the universe. What they found, if you zoom in on these 42 supernovae, it took 2 teams of about 40 astronomers using the largest telescopes around the world at the time, about 5 years to find these 42 supernovae. They found that these 42 supernovae were actually slightly fainter than you would expect if the universe was just expanding at a constant rate. And so that led to the conclusion that the universe is accelerating. It's actually increasing in the speed of its expansion over time. And what that means is that the universe all the space in the universe must be permeated by what has been called dark energy. It's dark because we can't see it, and it's energy because it's causing the universe to accelerate. So this was a huge discovery that led to overturning a lot of assumptions, a lot of expectations from over the past 100 years of what the universe actually looked like. And I wanted to show this picture basically just to show you that this led to the Nobel Prize in 2011, and it is proof that astronomers will wear suits if given the right opportunity. So, supernovae, 42, it took a lot of time to detect 42 supernovae, but actually supernovae, if you could observe all of the supernovae going off in the universe at once, you would be able to find about 10 supernovae every second. You can see here, this is kind of a simulation showing what they look like. They gradually increase in brightness and then they slowly decrease over time. LSST will not be able to detect all of these supernovae, all of the supernovae in the universe, but it will be able to detect a lot more than 42. And so what I'm showing here is a plot. These are all of the potential models for the universe that are consistent with those original 42 supernovae. And you can see that the conclusion that the universe is accelerating is actually, it's reasonably good, but there's a couple supernovae that contradict this, and it's actually, there's a 1% chance statistically that the universe is not accelerating if you just look at this data. Now what if you're able to detect a lot more supernovae? In that case, you would actually be able to significantly improve the measurement of dark energy. And not only does this increase the significance just of the measurement of dark energy, but it increases, this means that we can test different models for what is this dark energy, what does it mean? If we can figure out, is dark energy causing the universe to expand at a different rate in that direction versus that direction? We can actually do that if we have this many supernovae. And so that's one of the goals of the LSST. Now I'm going to very subtly switch gears and move away from supernovae to asteroids. Here's a map of the orbits of all of the known asteroids within the past couple of years or so, showing an animation showing their orbits, the orbits of the asteroids that lie in the asteroid belt between the orbits of Jupiter and Mars, roughly. You can see, as I showed before, yes, no, this is not real time, that there's a lot of asteroids that are kind of whirring past, down towards the Earth, down towards the Sun, past the orbits of the Earth. And so that has obvious implications. Every 65 million years or so, that could lead to big changes on the surface of the Earth, or even more frequently, an asteroid roughly the size of about a football field or a little less will hit the Earth and can cause about, in the case of this asteroid that crashed over Siberia, can flatten about 800 square miles of trees. And so these are commonly referred to as I guess, city killers. These collide with the Earth once every few thousand years. And so what we need to do is map these, identify their orbits, and be able to predict whether they're coming close to the Earth. In addition, scientifically, less practically, we can use something like LSST if we could map the orbits of the asteroids out beyond the orbit of Neptune. The orbits of these objects could potentially be perturbed by another planet. And so if there is indeed a planet 9, such as what I show here, the LSST has a fairly decent chance of detecting it. So I should say, LSST is going to detect 10 to 100 times more asteroids that have already been detected. Roughly 70 to 80% of those city killers that I mentioned. And so on a practical sense, LSST is going to detect, LSST has the potential for saving the Earth. Questions at the end. So finally, I talked about two things that we're going to detect by looking at the variable sky with LSST. There's a large number of other things, including variable stars, stars that flare, supernovae, which are shown here. So this plot shows how long an object appears in the sky if it explodes versus how bright it is. And so we know about a whole lot of things. However, there's this big space that we don't know about. So LSST has the unique capability of identifying things that we have no idea whether they exist or not. And so it's this unique opportunity science that LSST really provides as well. One of the examples, I guess many of you guys have probably came to the Astronomy on Tap last month, that talked about gravitational waves in LIGO and the detection of gravitational waves from the merger of two massive black holes. LSST could potentially provide targets of opportunity, these gravitational waves could provide targets of opportunity where we could point LSST in their direction and see. Right now we don't know, we've detected their gravitational waves, so essentially we can hear them, but we don't know if they make any light. And so LSST will be able to tell us whether these things make any light and whether they're actually, that'll help us figure out if they're actually due to black holes colliding. And finally, there's still some debate about this. No one's actually done the detailed calculations, but LSST does have the possibility of detecting many more potential planets around other stars as those planets pass in front of their stars and cause the star's light to periodically decrease. And so it's thought that LSST could detect thousands of Jupiters around stars throughout the Milky Way galaxy. And I'm going to end it there. I should say some of the slides in this talk were taken from Andy Connolly's TED Talk. Andy Connolly's a professor at the University of Washington, and you guys should go. Any of you who are interested in learning more about LSST can go view his TED Talk to get more information. Thank you.
Okay, got it.
Question?
Okay, so a couple slides ago, we were talking about LSST decision past Neptune. Right, so how does our atmosphere affect that?
Thank you so very much.
How does the atmosphere affect this? The Earth is a tiny, tiny dot. It would be microscopic here, and the atmosphere from the Earth doesn't have any effect on this.
So we're using the LSST, right?
Yes.
But earlier you said it does.
So, okay, so let me try to answer that. So, objects like this potential planet 9 and objects in the Kuiper belt out beyond Pluto's orbit are probably bright enough that we will be able to detect them quite easily, whether or not their light is being blurred by our atmosphere or not. The things that are hard are the things that are really far out and really small. And there, the atmosphere actually blurs the light so much that they might just get washed out. But if we're careful and if we stack our images together like we talked about, and we go deep enough, we can actually detect more of them.
Any more questions about this talk or the static sky?
So you talked a bit about dark matter. Can you explain dark matter as if I've had 6 beers?
First, let me ask, have you had 6 beers? Pretty close. Let me put dark matter this way. If you can explain, any of you out there, and that includes the astronomers, if you can explain what dark matter is really well, you can do the same thing as David over here and get a free trip to Sweden and a shiny medal. We know that dark matter exists in the universe. We know it has mass, hence we call it matter. We know it doesn't give off light, hence we call it dark. Beyond that, there's like 300 different models that purport to explain it, but we don't really know what it is. By measuring carefully the amount of it, we can maybe tie down those models better, and then experiments like the Large Hadron Collider are actually trying to produce dark matter through particle collisions. But I'm serious about that. If you can actually explain what dark matter is, you get a free trip to Sweden and you can shake the hand of the king.
Long sucks!
Are about equal. One, how do you know that? And two, does the gravitational light affect that? Does that affect your assumption that the further away you are, what the accelerated not as bright?
so this is a two-part question, and I'm going to go back to the slide that maybe we can use to talk about it. So the first part of the question is, how do we know that supernovae all have roughly the same intrinsic brightness, which is something I measured and which was a very important aspect of making this discovery.
Which one do you want?
I had a slide for that, but I cut it out. So actually, the way that this is known is that I didn't focus on these supernovae down here, but people have been meticulously mapping more nearby supernovae for 30 years before this discovery was made. And so they were able to look at, in this case, the supernova looks something like this. And you can do very fine, very detailed observations of them. And so what has been concluded is that there's a specific type of supernova. Supernova come in a variety of different types. Some come from the collapse of very massive stars. Some are thought to come from white dwarfs that are exploding. And white dwarfs that are exploding create supernova that have very well characterized brightnesses. And then the second part of the question involved lensing. And so if there's lensing throughout the universe, how do we know that that's not leading to the effect that's not leading to us believing that there's acceleration while it's not actually happening? And so I think my first answer to that would be that lensing, if it was going to do anything to the brightnesses of these supernovae, it would actually make them brighter rather than fainter. And what was observed here was that these supernovae were fainter than expected and not brighter. And the second answer is that I didn't talk about it, but there's observations from other different kinds of data. So the cosmic microwave background, for example, which has been now measured in very fine detail, provides very concise corroboration of this discovery of dark energy. And so there's actually been observations, including some of the observations that John talked about related to how galaxies cluster throughout the universe. There's actually a variety of different types of observations that all lead to that same conclusion now.
One more thing, and I'll be done. The increase in luminosity because of the lensing.
Raise your hand.
You're recording.
He's got a question.
Or do you
We'll be in a
do it
bowling.
So the supernovae are, so the question is how,
Let me take this one quick. So the question was, how exactly do we account for gravitational lensing? So basically you try a bunch of models and only one of them will fit the data correctly. And so the way you know that you got it right is because you can match the observation with your model. One here. So there's a couple of things. So the question was, writing a grant for the LSST, why did we get the money? And so I guess one thing I want to clarify, LSST is different from a lot of other telescopes. It's a survey telescope. It does a 10-year survey. You don't apply for data on it like you would for the Keck telescope or other telescopes. It's just doing that survey. But we had to get the money in the first place in order to build the darn thing. A lot of that money came from the DOE and NSF, so Department of Energy and National Science Foundation, who want to understand the history and fate of the universe, dark energy, dark matter, who want to find asteroids and find comets and do all of these things that LSST is going to do. And they have, as part of their research plans, they want to do all those things, and we happen to be able to do all of those things. separate, so that, I guess a part of that question was also like, is it also for saving the Earth? We do in fact have some money from the Department of Defense because we're going to find these Earth killers and these city killers. So the Department of Defense provided some money because because Congress told them you have to find all these things, and they said, okay, well, let them do it. One more question, and then this will be the last one. And we'll hang around for a while afterwards. If you buy speakers beer, we might answer more questions.
What do you want the drink?
Is there an attempt to actually measure the force of dark energy versus the force of dark matter? And this question of the big crunch versus the accelerated universe, is there any way to like try to calculate the balance of dark energy against the force of dark matter?
That's an excellent question. So the question is there any attempt to measure or understand the balance between dark matter, which pulls the universe together, and dark energy, which causes it to accelerate? And the actual answer to that is yes, there's been an extensive effort to measure both of those, and through all of the different kinds of data that I mentioned from a previous question, that's actually been understood pretty well, and it's now understood that there is more dark energy in the universe than there is, in essence, the universe is going to keep expanding forever. It's going to keep accelerating. The universe is going to end in a whisper and not a crunch.